PDF, please.
Okay, we'll start part 2. And now that I've covered some of the very basics about convection, I should say that all these simulations you saw, well, actually I did have some examples, but if you reverse the boundary conditions, make the top hot and the bottom cold, you'll get gravity waves. What will happen is if you want them to continue for a long time, you have to keep exciting them one way or another. You can, or you just give it a ping and it will eventually die out. But anyway, today, this part 2, I want to talk about, well, I should say this. I had this slide in here before I realized that Fran was going to give such an excellent summary. But these are a number of planets and satellites that have magnetic fields or had magnetic fields. And there's an article that Sabina Stanley and I published quite a while ago. And it talks about, or does a survey on the various models. So Fran was telling us mainly about the observations of the planetary magnetic fields. This article talks about all the various computer models or suggestions about how the different dynamos work in these bodies, if you're interested. But I'm not going to talk about all that today. I'm going to talk about the geodynamo and the Jovian dynamo, mainly Jupiter. So, as I'm just saying here, the geodynamo, you might consider magnetic seasons, not seasons due to orbital motion, but due to non-periodic magnetic dipole reversals. So we'll talk about that. And as Fran was also saying, the Juno mission and also the Cassini, the grand finale part of the Cassini mission to Saturn, will, starting next year, start sending us information about the very about many things, but in things I'm interested in are the gravity and the magnetic field in the interior of these bodies. I'll talk a little bit about that later. So just to put everybody on the same page, and again, Fran gave you some information earlier this morning about the interior structure of the Earth. This is just a very simple schematic. The outer region here is solid mantle. It's really not solid. It's undergoing mantle convection, but at 1,000,000 times more slowly than convection in the fluid core. So when you're studying convection in the core, you assume the mantle is a solid, not moving. You also assume it's a perfect insulator. It really isn't, but the electrical conductivity in the mantle is very small compared to what it is in the core. So the approximation is always, or usually made that this is an insulator. The typical time scale for a turnover, for example, tectonic plates sinking and falling to the core mantle boundary and then eventually plumes coming back up again, that time scale is on the order of what? Does anybody have an idea? How long is a typical cycle in the mantle? Want to make a guess? Yeah, hundreds of millions of years. Maybe a rough average would be something like 400 million years. The typical cycle in the fluid core, now convection is very complicated, but if you just used average fluid velocities to go around once, how long would that roughly be? So it's about 1,000,000 times faster, so on the order of a few hundred years. The fluid here is moving on the order of a millimeter per second, which will give this turnover time of roughly a few hundred years. So a millimeter per second is 1,000,000 times faster than the mantle flow, but it's still very slow compared to things we're used to, the winds on the surface of the Earth or the ocean flows. So all these different regions have very different material properties and time scales and physics and everything else. And then the interior, as Fran was saying, is a solid inner core. That may have only been around for the last couple billion years. It's not clear. Initially, this was all hot and all fluid. And at some point, the Earth cooled down to a point where the pressure was great enough to actually force the iron to start to crystallize. And like Fran was saying, it's easier for, according to mineral physicists, it's easier for the iron in this composition here to plate onto or solidify and plate onto the inner core than it is for the lighter elements. The lighter elements may be, it's not really known for sure what they are, but the suspects are oxygen and sulfur and carbon. So what happens is when iron in this mixture plates on to the existing inner core, a greater concentration of lighter elements is left behind in the fluid because more of the iron plates on and not the lighter elements. So that's a source of compositional buoyancy, and that's where the compositional equation is used. And in fact, most people think now that that's much more important, well, much more, maybe 3 times more important than the thermal buoyancy. But but in addition, the phase transition from liquid iron to solid gives off some latent heat. So the fluid also heats up in that process, the parcels that are right next to the inner core. So there's 2 sources of buoyancy. There's thermal buoyancy, the fluid heats up and expands a little bit, and there's an additional higher concentration of lighter elements, compositional buoyancy. And for those provide the buoyancy forces for it to rise in radius, and then the fluid viscosity is really small. It could be as small as water, even since the density here is about 10 times the density of water. And it's very different from the mantle where the viscosity is maybe 20 some orders of magnitude greater. So that you have very different regimes here. But here, because the viscosity is so small, Coriolis forces are really important. The rotation rate of the Earth is a huge effect. It has essentially no effect in the mantle because the viscosity is so large, the viscous terms are overwhelming any Coriolis force. And so when the buoyant fluid rises, it's going to feel these Coriolis forces and produce very helical type trajectories. And that's what's needed to generate magnetic field. It's basically the kinetic energy of this motion. First you have gravitational potential energy changing to kinetic energy then changing to magnetic energy by distorting the existing magnetic field.
So the rotational rate of the Earth core should be different from
It probably is. I'll talk about this in a few minutes. We actually predicted that with a computer simulation, and it got some seismologists working on it, and many seismologists think they are seeing that different rotation rate. But I'll talk about that in a little while. Oh, how do we get the composition? We don't. We guess. So the question is, how do we know what the composition of the fluid is? We know it's not pure iron based on gravity measurements. Basically, it wouldn't. Pure iron would be much more dense. But it's mineral physicists that enter the game. Then they tell us what lighter elements would most likely have sunk through the mantle into the iron core. So I don't even specify what those elements are. What I do is I say I have a variable that is sometimes we call the mixing ratio. It's basically the density of the light elements divided by the total density. And so that variable is what I try to evolve in 3 dimensions. So there's a source of that at this boundary, and there's a sink. It accumulates here. Okay, so I drew these magnetic field lines, this very simple schematic dipole pattern, the way the field looks like today. This, again, something that Fran mentioned, that the magnetic fields are inward at the north geographic pole. So this is the north geographic pole, the south geographic pole. That's just determined by the rotation rate. So I'm assuming that the equator's here, and this is the northern hemisphere and southern hemisphere, and it's rotating like my fingers. So that just defines what the north and south geographic poles are. But by tradition, a magnetic field entering here is a south magnetic pole. And because a compass, the north part of the compass needle points to our south magnetic pole. So this is actually a south magnetic pole, a north magnetic pole here. And when there is a magnetic field reversal, the directions change, obviously. So that's just it's the change in the axial part of the dipole part of the field. Okay. And then the big question is, how does that happen? Why does it happen? How often does it happen? So let me see here. So here, this is something also that Fran showed, just a record of reversals starting from today, going back in time. These are millions of years, continuing here back 160 million years. This is roughly the time it took for the Americas to separate from Europe and for the Atlantic Ocean to open. So these records are mainly from measuring the magnetic field direction in the bottom of the ocean, on either side of the mid-Atlantic ridge that separates. And the dark regions are called the normal polarity. That's the polarity we have today. The light regions are called the reverse polarity. And so you can see there are quite a few reversals, but it's not nice and periodic like it is for the sun. First of all, the time between the reversals, like Fran was saying, is on the order of several 100,000 years. But there are some that occur more frequently than that. Some periods that are tens of millions of years long. These are called supercrons. And there's a lot of people trying to understand why the frequency changes so much. And it probably has something to do with mantle convection, because the rate that heat is coming out of the core and where it's coming out of the core, what latitude and longitude, depends on what the temperature pattern is at the base of the mantle, at the core mantle boundary. Where subducting slabs are sitting on the bottom of the mantle, on top of the core, where they are, they're still cold. Even though it took 200 million years to get there from the surface, they're still cold compared to the surroundings because the thermal conductivity is so small and these slabs are so large. So they're cold, and then the core below sees a colder mantle under these slabs, and more heat can be conducted through there. So the pattern of heat flux influences the type of convection that will occur, which makes some patterns are more likely to disturb the magnetic field and cause reversals, and others are more stable. Okay. You can also look at just the more recent present back to just 3.8 million years. Again, that's the normal period. This was the last complete reversal about 780,000 years ago. And then these are reversals. But what we're plotting here is some measure of the magnetic field, or the dipole part of the magnetic field. So if you have good records in this recent time, people can measure the intensity. And notice that there are many times when the intensity drops significantly, but it always drops significantly during a reversal. But the converse is not true. In other words, when you have a drop in intensity, it doesn't necessarily mean there's going to be a reversal. It probably was an attempted reversal. I'll show you a movie showing there are many attempted reversals for every one successful one. Okay, so those are some of the observations. This is a snapshot of one of my first geodynamo simulations. Again, this is the core mantle boundary in the model. The mantle is out here, but it's basically the same as space. I'm assuming it's an insulator. And you can see that outside the core, the field is fairly dipolar structured, very dominantly dipolar structured. The rotation axis is right through here. You can sort of see this cylindrical structure. That's because the inner core is right here, and it sets up a cylindrical type flow, even where it's not present, here and here. And that cylindrical flow tends to twist the poloidal field into toroidal field. So you have, it's called the tangent cylinder, a cylinder that is tangent to, well, it has an axis that's the same as the rotation axis of the Earth. And you have a region outside that where much of the magnetic field is generated, and on this surface. So this is just one time step during a long simulation. I should mention that these lines are just graphical, as I said before. I don't use them in the calculation. Everything in the calculation is a continuous magnetic field. I'll go over this very quickly. These are observations. I think Fran also showed this plot in the year 1980? Do you see it? Right there, 1980. So this is what the magnetic field looked like on the surface in 1980. The reds and yellows represent outward directed magnetic field. The blue represents inward. And this is the entire surface of the Earth. The equator is through the center. This is the north geographic pole, the south geographic pole. And then if you take this field and, assuming the mantle is an insulator, you can mathematically project it down to the top of the core, and you get this structure. And this structure will be more complicated because it's closer to the source. This dipole structure decays like 1 over r cubed. And the quadrupole will decay as 1 over r to the fourth, r being the radius. So the higher the degree, the smaller the scale structure, and the faster it decays with radius. So it looks very dipolar at the surface because you're quite a ways away from the core. The closer you get to the core, the more complicated it is. These are simulations we did, Paul Roberts and myself, back in mid-1990s, and showing what a snapshot of our simulation looks like at the surface and at the core mantle boundary, assuming I'm only using spherical harmonics up to degree 12. Like Fran was saying, the Earth's magnetic field is only known to about 12 or 13 degrees because of the crustal magnetism overwhelms it at that point. So this is, so qualitatively you get similar pictures. We're not trying to get the exact one because we don't know the history of the Earth or the history of the fluid flow in the core. So we're just trying to get something that's qualitatively similar. And these are the same scales. But if I use, in this case, I was using degrees all the way up to 95, all orders and degrees up to 95. And then you see much more structure here, much more small-scale structure, almost like sunspots in a sense. They're concentrations of magnetic field. So when you see patterns of the magnetic field on the core mantle boundary that are this large, remember that you're only seeing the large scales. Surface doesn't change much, though. Okay. Someone asked, forget who, someone asked about the inner core rotation, superrotation. This is a small part of a long simulation, only 20,000 years. And it shows the rotation rate of the inner core in the model. The inner core is solid, but it's free to rotate and respond to torques, magnetic torques and viscous torques. And we try to make the viscous torques as small as we can to make it more and more realistic. But the magnetic torques are going to be relatively realistic. The field strengths are similar to what we see on the Earth, at the surface at least. So this is a plot of what the rate of rotation of the inner core is, degrees per year, relative to the mantle. And so you can see it goes up and down. It oscillates. on maybe a period of 75 years or so. But there's a drift, an eastward drift. The fact that this is positive on average means that this simulation is suggesting that the inner core, although it's wobbling, it's slowly drifting eastward relative to the mantle, so rotating a little bit faster than the mantle. And I remember we published this in 1995 or 6, something like that. And I didn't, I couldn't imagine anybody ever verifying it. So I only wrote about 2 sentences about it. But some seismologists at Columbia University had been looking at how fast seismic waves pass through the core, those that pass through just the fluid and those that pass through the fluid and the solid core. And they measured the difference in time, the travel time. And they found that the waves travel more slowly through the rotation axis than along the equator. So they said, well, if the inner core is actually rotating at this rate, they should be able to see a change over 30 or 40 years in this travel time difference. And although 30 or 40 years is not a big part of that whole cycle, they suggested that they saw some of this prediction. And so this is nice because a computer simulation just happened to produce a prediction, and somebody in another field, seismologist, picked it up and ran with it. Mineral physicists got involved because of the structure, crystal structure of the inner core determines these different speeds through the core, and it sort of grew, and many people started working on this problem. There are other seismologists that found that they didn't see any drift. They saw variations, but no drift. So that's sort of still an open question, and it'll be quite a few years before people can maybe pin that down. The closer they look, the more complicated they see what's happening. But anyway, that's an example of a computer simulation making a prediction. Another cycle are the dipole reversals. This is a simulation. Again, this is a simulation I did years ago. And at that time, we couldn't afford a lot of spatial resolution. And this simulation took about 9 months of my time. And I just kept running it. I was only running it on probably 20 processors at that time. And so then, what I'm plotting here, this is the north geographic pole, the equator, and the south geographic pole. And I'm plotting the location of the south magnetic pole. So it started off in this, it varied. It sort of, wanders around the pole. And for a long time, I was happy to get something that looked like a dipole. I never even imagined it would reverse. And I remember I was off giving a talk somewhere. And even when I'm traveling in the hotel, I log in to see what's happening every day. I basically look at some diagnostic numbers to make sure it was still running and didn't crash. But I remember coming back and noticing that the pole had reversed, and went back and saw the reversal. Now this looks like an almost instantaneous thing, but there are a large number of time steps. From this point to this point is something like 30,000 time steps. The computer updated the equations 30,000 times just to resolve this reversal. And then it stayed in this state for a long time, and finally it reversed again. So since then, we've seen many reversals, and many other people started doing these calculations with different models and starting to see reversals, and find that the frequency of reversals tends to depend on how you specify the heat flux at the core mantle boundary. It depends on a lot of other things too. But I want to show you a simulation. Again, this is the same simulation, but of that first reversal. And again, this is the equator. This is the entire core mantle boundary. So all the interesting stuff is happening below this surface. This is what the pattern of the field, the radial component of the field looks like. Reds and yellow is outward directed. Blue is inward directed. And it's complicated because you're at the core mantle boundary. And what I'm going to show you now is a simulation that the movie will span about 200,000 years. And let me get that started. There we go. So this is moving, and you can see that there's also a sort of a westward drift that's also observed on the Earth, mainly over Africa. But it's time dependent, very time dependent. You see the dipole structure is all this yellow and red in the southern hemisphere and blue in the northern hemisphere. But there's all these other poles, quadrupoles, octupoles, many different spherical harmonics involved in this. And what it will happen here is that very shortly, this is going to speed up by a factor of 6. So I wanted the movie to go more quickly. So there you go. So it's the same simulation. I just used 6 times fewer frames than I did before. So now you can sort of see the evolution. Darker colors mean more intense field, and sometimes it tries to reverse by getting rid of this dipole structure and being more uniform. So the fluid flows are very chaotic. They're always trying to twist magnetic fields and generate new magnetic fields, and sometimes those new magnetic fields are in the opposite direction of the original polarity. And also, when it tries to reverse, sometimes the amplitude becomes very small, just like in the observations. Like right now, the field is very, very weak, and it's all over the place, and you think it might reverse, but it doesn't. And this seems to happen in the Earth's record, paleomagnetic record too. It tries to reverse more often than it actually does. Again, it looks like it's all over the place here, and but it comes back again. So what it's going to do is, if this region in the north becomes red and this is blue, that would represent the dipole reversal. So again, you get a lot of red up here, but it dies out again. Okay, now watch the next time. Yes.
So presumably we can
There it
measure,
is.
Did it. We can measure the surface field, but how do we go about backing out the surface mantle boundary field?
The surface.
Because isn't that what you were plotting earlier? There's the magnetic field at the core mantle boundary.
This is the core mantle boundary field, yeah.
How do you do the downward continuation?
Okay, I'm going to show you a movie after this that shows both the surface and this at the same time. Now, you do that boundary extrapolation. Obviously, you only measure the field at the surface, but by assuming there's no electrical conductivity, you assume there's no electric currents, and that gives you a potential field. In other words, you can represent the magnetic field as a gradient of a potential. And once you do that, you have a boundary condition at one point, and you just expand in spherical harmonics. This will be a function of rate. It's the same thing you use for Gauss coefficients. You know, if you know what the magnetic field is at the surface, you can use the Gauss coefficients to expand into space above it. Well, you can do that because you're assuming it's a potential field. You're assuming the electric fields are so small. I mean, the electric currents are so small that you don't need to account for them. Well, the same thing below. You assume that the electric currents are negligible. So you can expand downward. So now the radius that you're at is smaller than the surface radius. So all those ratios are going to, you have a coefficient in that expansion that's the radius of the core divided by the actual radius you're interested in to some power, like L plus 1 or L plus 2. So when you're extrapolating downwards, that ratio is going to be larger than 1 because the radius is smaller than the surface radius. And so the field strength gets larger. But you can only do that accurately down to the core of the top of the core, the bottom of the mantle. Because below that, there are definitely going to be strong electric currents. I mean, you can do it mathematically, but it would make no sense.
So it's essentially like a potential field for surface models that we use.
Exactly, yeah, yeah. So, but this is only good down to the top of the core. Okay, so that showed that it reversed, and it tends to try to keep reversing. And I didn't run the movie long enough to actually capture the next reversal that it actually did occur.
You said this east to west convection, and you said it's particularly in Africa. What's causing this convection, and why doesn't it happen more for Africa?
I don't know. Everything's pretty chaotic even in the simulations. You think, well, you get a simulation that does the same thing, and then you look at the simulation, you got so much data over so much time. It's basically, you know, you throw up your hands and say it's chaotic. It's like trying to explain why a thunderstorm happened in Boulder, you know, one day. You know, it's all history and small perturbations. It's chaotic, but it's not so much convection. It's convection's occurring everywhere. It's more a phase velocity of the magnetic field and how the magnetic field is constructed and destroyed. Yes?
If you run a simulation identically again today, should it reverse at the same time?
Well, if I ran it on the same computer with the same initial conditions, it would. If today I would run it at much, much higher spatial resolution. And if I started with those initial conditions, probably it wouldn't, it'd probably have a different evolution. It probably would still reverse, but probably not at the same time. So, you know, you can't think of this as being an exact solution. It's because everything's approximate, because the equations are approximate, the numerical methods are approximate, and the spatial resolution is very approximate. So it's only meant to give you some qualitative feeling for how things work. So what I'm going to do now is show you that reversal again, but only during the reversal. And now this is what you just saw. I'm making it smaller because that's really the size, the relative size of the surface of the inner core, I'm sorry, of the core mantle boundary compared to the surface of the Earth, okay? And these are happening at the same time. You can see that this looks much more dipolar because it's further away than the core mantle boundary. So, but this movie is only going to span about 7,000 years around the reversal. And it's going to be going at the slower speed. So if you're on the surface of the Earth and this were happening, you'd see this type of thing happening over a period of 7,000 years. So there's the reversal. You saw that before, but it's much smoother and better, you know, more dipole defined.
7,000 years.
7,000 years, yeah. So the typical time that paleomagnetists see reversals in rocks and lava flows and various things is around 5,000 years. So there's some uncertainty there because you have to define what the beginning and end of the reversal is, because it's going to be sort of more chaotic and all of a sudden it swings a lot. So there's, you know, but roughly 5,000 years is an average. Now some of the reversals I've seen have done it in 1,000 years, and some have taken 20,000 years, and some have, you know, tried for 20,000 years and failed and went back to the original polarity. So there's a lot of variability. No two reversals we've seen are alike. That's one thing. You know, when we started this thing, people thought there must be one way it happens. Let's figure out that one way it happens. And then we started getting more of these reversals, and they're all very different. They take different amounts of time.
With them all being different and there being apparently random variations between one and the other, do you have enough simulation data to generate distribution functions of?
Yes. Yeah, there are papers we published showing lots of distribution functions of you know, how much time, say, the south magnetic pole spends in the northern hemisphere compared to the southern hemisphere, and how much deviation from the geographic poles, and those distribution functions, PDF functions, are depend a lot on how you set the problem up. We can't do the Earth very accurately because we can't get to low enough viscosity or thermal conductivity, so or we have enough resolution. So, and what the pattern of the core mantle boundary heat flux is, that's going to also depend, like I mentioned before, that will influence how chaotic the convection is, which will influence the frequency of the reversals. But we have papers where we change these parameters, and you can show different distributions and try to understand how changing the parameters affect the reversal frequency.
So I exhausted it.
Yes.
And of course, the question always is during this transition switch, how do you small the dipole become? My order will propagate on this point.
Yeah, in normal times at the surface, it's dominated by the dipole, the axial dipole. And during the reversals, by definition, the axial dipole goes through zero. It's in one direction, then it goes through zero to become, that's the definition of a dipole reversal. But the total dipole doesn't go through zero. There's an equatorial component. In other words, there's a dipole right on the equator. And usually during a reversal, there's several poles, magnetic poles on the equator. It's very, very structured. But your question is, if the total field will probably, well, in these simulations, they drop at least, the intensity drops at least by a factor of 10, and I've seen it drop much more than that. So, but it's not only the intensity that is important, it's the fact that now cosmic rays will be focused on the equator. That's where the poles are. And more of them will get through, but any focusing will occur on the equator, not the poles. And so that's where most life occurs. And so that's another potential problem. But apparently, I don't know much about how the cosmic rays will affect people, but the next time we get a reversal, we'll probably, the soonest I think a reversal will start will be maybe 2,000 years from now. And then it takes another 5,000 years maybe to complete. During that 5,000 years, it will probably be a lower intensity and a lot of cosmic rays. But I would think in 2,000 years, as long as NSF and NASA keep funding us, we'd have a way to figure out how to shield ourselves from those problems, or living on a different planet.
In that line of talking about the next reversal, you said earlier that the reversals are usually occur at the time that the dipole, you see this weakening in the dipole. And remember from that plot, it looked like the dipole was really very strong. It has been very strong for quite some time. So, we would see that signature of a very weak dipole occurring before the reversals?
Oh, yeah, you start seeing, in fact, it has been decreasing. It has been decreasing for the last few thousand years. And there's better measurements over the last 20 or 30 years with satellite surveillance. So the field intensity is decreasing. Sometimes you see articles about that. The field is decreasing, and when it gets small, there's a reversal, and then I get a bunch of emails saying, well, should we start putting more food in the refrigerator or whatever? And I say, well, it's a little misleading, because in the past, several thousand years ago, the intensity was much higher than the average. We're down to about an average. If you take an average of the field intensity through paleomagnetism over several million years, we're down to about that average. But it's still decreasing faster than it would be by just magnetic diffusion, decay. And so there are processes occurring that are destroying the current field, and that's how these reversals occur. But even at that rate, it probably will be on the order of 1,000 years or more before we would really say, well, a reversal is happening. And it's just as likely, or maybe even more likely, that it will keep decreasing for 1,000 years and then start increasing without a reversal. Even though it's been 780,000 years, which is longer than the average, it's just because it's been longer than the average doesn't mean the probability is higher. So, but it won't happen in our lifetime. So what I'm going to do now is show you yet one more version of this reversal. In this case, I'm going to show you not what I did in the previous movie. You saw what the magnetic field is at the core metal boundary and at the surface of the Earth. And I just showed the radial component. Now I'm going to show, this is the outer fluid core. Surface is out here. I'm going to show on this side of the plot magnetic field lines. Oh, I should say this is all now averaged in longitude. Computer simulation is done in 3D, but to make the graphic a little simpler to see, I've averaged everything in longitude. So things are not going to be quite as time-dependent or structured because a lot of it gets averaged out. And green here represents clockwise. In other words, initially the field is directed inwards at the north geographic pole and outwards here. And I'm going to represent that by a green color. When it changes and reverses, I'm going to make those contours look yellow. So that will be the reverse part. So this is the poloidal field on this side. This is the toroidal field. These are not magnetic field lines. They're contours of the strength or the intensity of the field. Red and yellow represents an eastward component, in other words, into the screen, and blue represents an outward or a westward component. So you have a strong toroidal field here, and you'll see through this simulation that both this reverses and this reverses. So again, this will be the same 7,000 years that I ran just previously, but now you're looking at it inside the core where all the action occurs. So it's still time dependent, even when averaged in longitude. But every once in a while, the fluid flow tends to twist field lines in a different direction and tries to produce the opposite polarity, at least locally. And you'll see how this happens. This is just one example of a reversal. So right there is a reverse polarity. And then it almost dies out. And that's usually what happens. It dies away. But this time, for some reason, the flows are continually building this up. And if you're sitting on the surface of the Earth, you say the reversals have already completed. You see, the original polarity is still locked into the solid inner core. It's there, it can only diffuse away, and that takes several thousand years. So it's slowly diffusing away, and the new polarity is slowly diffusing into the inner core. So, and once it's in there, it's got more resistance to reversal. And many times, because it takes so long for the original polarity to diffuse out of the inner core, the original polarity has an advantage. And many times it tries to reverse, but eventually it comes back to the original polarity. And you can see that both the toroidal field also reversed. So that's what I want to show you for the Earth. Go ahead. Yes. Yeah. So right after right while it's reversing, the poloidal field is very small, and it's the shearing of the poloidal field that generates the toroidal field. So as the poloidal field reverses its sign, then it's starting to destroy the toroidal field because it's shearing in the opposite direction. Okay, so now let's switch to Jupiter. And how much time do I have?
10 minutes.
Okay, probably can do it in 10 minutes. So this is for Jovian dynamos like Jupiter and Saturn, in particular Jupiter. You've seen the banded cloud structure. These clouds float on a banded wind structure, a zonal wind structure that blows east and west relative to the mean rotation rate. And this is a typical plot. Have you seen this before? Anybody seen this plot of the zonal winds on the surface of Jupiter? What you do is you take an average surface rotation rate. Oh, actually, it's not that. They take the rotation rate of the magnetic field, which is close to the average rate of rotation on the surface. You call that 0. And then you plot wherever these clouds are moving eastward relative to that mean rotation rate, it's a positive zonal wind. And westward would be a negative. So in the equatorial region, you have large eastward flow, eastward jet, and then retrograde on either side. Retrograde, now, when I say westward, I mean everything, if you observe this in the inertial frame, everything's rotating eastward. That's right, it's like differential rotation on the sun. But more complicated because the sun just has a strong equatorial jet and then it peters out at the pole. This has many, many bands. And so it's in a different parameter regime than the solar dynamo. That's what it looks like for Jupiter. Saturn, this is a nice actual movie of Saturn by one of the Voyager spacecraft. I forget which one. But as it was approaching Voyager many years ago, it would take a snapshot of the surface here, these cloud formations, every roughly 10 hours. It's a 10-hour rotation period. But so by taking it at the same frequency as the rotation, it's as if you're in the rotating frame. So now the movie is like being in the rotating frame. You're going to see well, first of all, at the equator, you'll see this moving much faster. So the same type of thing happens on Jupiter. These will be spinning faster, and a lot of these features will be moving eastward. Some will actually be moving westward because it's in the rotating frame. So just to show you what an actual movie of this planet is. So that's differential rotation, banded latitudinal structure of Saturn. So that's what we're trying to understand. A big question is how deep below the surface does this penetrate, both on Jupiter and Saturn? Is it really just a shallow atmospheric dynamics that's maintaining that, or does it penetrate deeper? That's an ongoing debate that maybe Juno and Cassini will be able to help us understand. So this is a simulation I did quite a few years ago, showing what I did here is just simulated the outer, I think it's roughly 25% of the radius, because that's where we suspect most of the action is occurring. Red means the winds are blowing eastward, and blue means they're blowing westward. So you get sort of a banded structure for this. I call it a thin shell because really it should go down close to the small inner core. But when you do this, you get, well, if you do it for Saturn, this is the simulation, and on the same velocity scale, this is similar to what I showed you for Jupiter. This is the Voyager measurement of the winds on Saturn. They're actually stronger than Jupiter and quite broad, with banded structure at high latitudes. And these data points are the Space Telescope, more recent measurements. So either the Space Telescope is seeing something different or different cloud level than Voyager did, or there was a significant change in the wind speed over many years. But the simulation shows qualitatively similar structure. But when I do a more realistic simulation where I do almost a full sphere, and this is the small inner core, I still get banded structure, but it's very broad. And at the surface, it doesn't look like what you see on Jupiter. This is what it would look like in the equatorial plane. Yellow means it's eastward, blue means it's westward. And this is what it looks like on the surface, an eastward band here, westward, eastward. So this is discouraging because I thought I was doing something more realistic, and I got something looking less realistic. So there's a question here about what's happening, and it might be that this phase transition that Fran was talking about, the pressure ionization of hydrogen, occurs right about this level, and below that, hydrogen is a good electrical conductor, and above that, it's close to an insulator. It goes from an insulator at the surface and almost increases exponentially with depth to a very high value when it's completely ionized or almost completely ionized. So this is built into the model. My electrical conductivity is about 5 or 6 orders of magnitude smaller at the surface than it is at this depth. So almost all the magnetic field is generated in about this region. And above that, it looks like an insulator. But I still don't understand why I don't get more bands at higher latitudes. But going with that, this is the magnetic field structure I see. I see that if you're far enough away, you still see much of the dipole. But with Juno, we'll get close enough to be able to see banded structure in the magnetic field, up field here and down here, and up here and down. In other words, if you're close enough, you can hopefully see some banded structure if it exists. So if it exists near the surface, Juno should be able to detect that. In addition, I solved for the perturbation in the gravitational field. And I'm looking at, these are all gravitational perturbations at a radius of just 7% of the radius above Jupiter's radius. So this is the closest approach, roughly, that Juno will get. It has a very eccentric orbit, polar orbit. I'll show you a schematic of it momentarily. But this is the closest it will get. And at that distance, in my simulation, I see a banded structure in the gravity. This is the radial component of the gravitational perturbation. Blue meaning it's negative, meaning it's pointed downwards. There's a stronger gravitational acceleration downwards relative to the average. And this is the colatitude component in latitude and longitude, latitude. So this banded here. The longitudinal component, east-west, has very little banded structure. But you see something similar in the magnetic field. This is just the same as this picture, basically. That's a 3D representation, and this is sort of a 2D representation of the radial component of the magnetic field. Upward here, downward here, upward, etc. And the latitudinal. If I go just one radius of Jupiter above the surface, I don't see this at all. I just see a dipole. So that's how critical it is. This is about 5,000 kilometers above the surface of Jupiter. That's the closest approach. If I go, say, half the distance to Io's orbit, I don't see this in the simulation. So it's very important for the spacecraft to get this close to be able to see this signature. So here's a schematic. Juno was launched, I forget now, 5-6 years ago? 2011, okay. And it's going to get to Jupiter roughly about a year from now.
4th of July.
4th of July, okay. And then it's going to go into orbit, a very eccentric orbit, meaning that this is a very elliptic orbit. And this is the axis of rotation. It's going to be a polar orbit to avoid a lot of radiation damage, I understand. So it's going to go around and be, I think it's going to do 33 different orbits over a period of a year. So each orbit is about 11 days long.
It's changed now 2 weeks, 14 days. So.
Oh, it is 14 days. Okay. And but the interesting things will happen when it gets really close to the surface here and can measure both the gravity and magnetic fields and many other things. Okay. But most of the time it's going to be spinning out here going very slowly, and then it goes out here and then zips around. So, but it'll give us measurements that we haven't seen before. So this is my final slide, and my predictions based on my calculations, saying that there may be 3 different possibilities. One is if Juno and Cassini, which is going to be doing this at Saturn at roughly the same time, if they see no banded axisymmetric structures in the magnetic and gravity data, in other words, unlike what I've seen, if they see no banded structures, then that argues that the zonal winds that are seen in the clouds or on the surface are probably just surface features, and that the wind structure, that strong wind structure, doesn't penetrate very far below the surface. Because if it doesn't penetrate very far below the surface, it won't be very strong at place where the electrical conductivity is very strong. And that's where those winds could affect the structure of the magnetic field. The winds near the surface aren't going to affect it because it's basically an insulator. It can be blowing very strong, but the magnetic field doesn't care. Also, if no banded structure is seen in the gravity field, that suggests that very little mass is participating in this wind. So if it's deep winds, then there's more mass, a bigger gravitational signal. So that would be a null conclusion, and the climate modelers who have been claiming that all these winds are just surface features, they would win the prize. So here is another possibility. Maybe you get just broad-banded axisymmetric structures like the ones I've been simulating. And that would suggest that near the equator, you have winds that penetrate fairly deep, down to the conducting region where the magnetic field is generated. But at higher latitudes, those small bands maybe are very shallow. And the other extreme is you might see bands at all latitudes. that would represent even high latitude bands are deep. The problem is that because of this trajectory, the high latitudes are not going to be as well resolved because the closest approach is right near the equator. So it's possible that there is a signal at high latitudes, bands there, but maybe Juno won't get close enough to actually clearly see them. So, any questions?